This is Assistant Professor Vishnu from Department of Mechanical Engineering, Rajgiri School of Engineering and Technology, Kakinada. Welcome back to the lecture series on Basics of Mechanical Engineering. In my second lecture, I will be discussing about the laws of thermodynamics. While preparing this lecture, I have referred textbook on Engineering Thermodynamics by PKNR. As you know, the different laws of thermodynamics are the Zeroth law, the first law, and the second law of thermodynamics. So, now we will be starting with the Zeroth law of thermodynamics. What is the Zeroth law of thermodynamics? If two systems are in thermal equilibrium separately with a third system, then they can be said to be in thermal equilibrium with each other. Now, if A is in thermal equilibrium with C and B is also separately in thermal equilibrium with C, then we can say that A and B are in thermal equilibrium with each other. The main application of Zeroth law of thermodynamics is in the measurement of temperatures, that is, they are used in thermometers. Now, coming to the first law of thermodynamics. You already know that the first law of thermodynamics is also known as the law of conservation of energy. That is, the energy can neither be created nor be destroyed, but can only be transformed from one form to another. There are several applications of first law of thermodynamics. Now, coming to the first application, that is, the application of law of conservation of energy, or the first law for a closed system undergoing a cycle. Here, for a system operating in a cycle, the net heat transfer is equal to the net work transfer. The closed integral of delta Q will be equal to closed integral of delta W. Now, going to the second law of thermodynamics. Before explaining the second law of thermodynamics, we must know what are cyclic devices. As you already know, there are two cyclic devices which are used in this second law of thermodynamics. They are the heat engine as well as the heat pump. A heat engine is a device working in a cycle in which there is a net heat transfer to the system and a net work transfer from the system. An example is an IC engine, and a heat pump is a device which is working in a cycle in which there is a net work transfer to the system and net heat transfer from the system. And we know that for continuous heat or work transfer, a device should work in a cycle. Now, coming to the thermodynamic model of heat engine. Before explaining the second law of thermodynamics, we should know what is the thermodynamic model of a heat engine as well as the thermodynamic model of a refrigerator or a heat pump. So, the thermodynamic model of a heat engine is represented by this diagram. As you can see, there are two reservoirs. That is, the reservoir at high temperature as well as a reservoir at low temperature. And as you can see, the heat is transferred from the high temperature reservoir to the heat engine, and a certain amount of heat is rejected to the low temperature reservoir, which is represented as QL, and the work output is represented as W. The equation for efficiency of a heat engine is given as eta equal to maximum work obtained divided by total heat supplied. So in this case, we can replace this maximum work and the heat supplied as you can see from the diagram, QH is the amount of heat which is supplied to the heat engine. So the equation will be transformed into eta equal to net work, which is the W divided by QH. This W is the difference between QH and QL. So eta will be transformed into QH minus QL by QH, which can be replaced in terms of temperature as TH minus TL by TH, which is always less than 1. Now, coming to thermodynamic model of refrigerator cycle. As you can see, a refrigerator always transfer heat from a low temperature reservoir to a higher temperature reservoir with the aid of an external work W. So in this case, the heat which is taken from the low temperature reservoir or the whole body is represented as QL, and the heat which is supplied to the higher temperature reservoir or the higher temperature reservoir is represented as QH. Now, coming to the performance parameter in terms of a refrigerator, the performance parameter used is coefficient of performance or COP. What is this coefficient of performance? Coefficient of performance is defined as the desired refrigerating effect divided by work input. So in this case, COP can be replaced by the desired refrigerating effect for a refrigerator is the amount of heat which is sucked from the low temperature reservoir, that is QL. So the equation transforms to COP equal to QL, which is the desired refrigerating effect, divided by work input. We already know that this work input can be replaced by QH minus QL. So the equation becomes QL divided by QH minus QL, which is equal to TL divided by TH minus TL when we are transforming to the terms of temperature. Now coming to the thermodynamic model of heat pump. As we have explained, in the terms of a refrigerator, the refrigerating effect is the amount of heat which is sucked from the low temperature reservoir. Whereas in the case of a heat pump, the refrigerating effect is the amount of heat which QS supplied to the high temperature reservoir. Now coming to the thermodynamic model. Here, as you can see, the heat pump is represented in the middle section. Then there are two reservoirs, which is the high temperature reservoir having a temperature of TH and a low temperature reservoir having a temperature of TL. And the heat which is sucked from the low temperature reservoir is represented as QL, and QH is the heat which is given to the high temperature reservoir. And for transferring this QL to QH, we require an additional work W. So the equation transforms to COP equal to the refrigerating effect for a heat pump is represented as QH divided by W net, and W net is replaced by QH minus QL, and transforming into terms of temperature we get TH divided by TH minus TL. And rearranging, we can see that the COP of a heat pump will be equal to COP of refrigerator plus 1. Now coming to the second law of thermodynamics. As I have already explained, before coming to the second law of thermodynamics, we should know the cyclic devices, which are the heat engine, heat pump, and the refrigerator. Now, I will be explaining the second law of thermodynamics. There are two statements for the second law of thermodynamics. The first statement is the Kelvin-Planck statement. This Kelvin-Planck statement is basically used for heat engines. The Kelvin-Planck statement states that it is impossible to construct an engine working on a cyclic process whose sole purpose is to convert heat energy from a single thermal reservoir into an equivalent amount of work. It can be simply summarized as the Kelvin-Planck statement states that a heat engine cannot convert the entire heat to work. That is, a certain amount of heat should be rejected to the low temperature reservoir. So the first diagram is impossible according to second law of thermodynamics, and this can be replaced as a high temperature reservoir with temperature T1, low temperature reservoir with temperature T2, and heat engine at the middle section. When an amount of heat Q1 is the heat supplied to the heat engine, and Q2 is the amount of heat which is rejected to the low temperature reservoir, and the net work output obtained is represented as W equal to Q1 minus Q2. Now coming to the second statement of second law of thermodynamics, which is the Clausius statement. This Clausius statement is usually used in refrigerators as well as in heat pumps. The Clausius statement is that it is impossible for a self-acting machine working on a cyclic process to transfer heat from a body at a lower temperature to a body at a higher temperature without the aid of an external agency. Can be simply summarized as it is impossible to transfer heat from a lower temperature reservoir to a higher temperature reservoir without the aid of an external work. That is, in these diagrams, the first diagram is impossible according to second law of thermodynamics, as here the heat from a low temperature reservoir is transformed to high temperature reservoir without an external work. So this is impossible according to second law of thermodynamics. And the second diagram shows that the heat which is transformed from low temperature reservoir to higher temperature reservoir only because of the area of an external work W. Now, coming to the topic entropy. What is entropy? Entropy is the measure of irreversibility of a process. For explaining the entropy of a system, we define the efficiency as eta equal to 1 minus Q2 by Q1. This can be represented as 1 minus T2 by T1. And we know that Q2 by Q1 it can be represented as T2 by T1 according to absolute thermodynamic temperature scale. Now rearranging, we get Q1 by T1 equal to Q2 by T2. And subtracting, we get equal to 0. The cycle of Q by T will be equal to 0 for a Carnot engine. That is the cycle. Closed integral of delta Q by T will be 0 for a Carnot engine. As you know, the Carnot engine is a reversible cycle. So, this closed integral of delta Q by T equal to 0 implies that this delta Q by T is a property, since for any property the closed integral will be equal to 0 for a reversible process. This delta Q by T is known as a new property which is called entropy, which is represented by S. So delta Q by T will be equal to TdS, and Q will be equal to integral of TdS. That is, the area under the TS diagram will be always the net heat transfer. So entropy is a measure of molecular disorder or randomness. It is a point function or extensive property. And the formula for change in entropy is represented as ds equal to integral 1 to 2 delta Q by T. Now coming to the various thermodynamic processes. The various thermodynamics processes are, the first one is the isochoric process or the constant volume process, which is represented by a vertical line in a PV diagram. And the next one is the isobaric process or a constant pressure process. It is represented by a horizontal line in a PV diagram. Then comes the isothermal process where temperature remains constant. Then the reversible adiabatic process, which is also called an isentropic process where entropy or S remains constant. And the last one is the polytropic process. Now coming to the efficiency of a Carnot cycle, which is a reversible cycle. As you know, eta was derived as 1 minus Q2 by Q1, which is equal to 1 minus T2 by T1. So efficiency of a reversible heat engine in which heat is reserved solely at temperature T1 from a high source reservoir and the heat is rejected solely to temperature T2 to a heat sink reservoir. Then the various processes in a Carnot cycle are represented as shown here. That is, the first one, which is an isothermal expansion, is represented as the red line. Then comes the adiabatic expansion, then isothermal compression and adiabatic compression. So we can summarize as the Carnot cycle comprised of 4 reversible processes, 2 isothermal processes and 2 adiabatic processes. Now coming to the analysis of Carnot cycle. As we have already explained, there are 4 processes for a Carnot cycle. The first one, which is the isothermal compression. As you can see, it is represented using a piston cylinder arrangement, and since this process 3 to 4, which is the isothermal compression, is a constant temperature process, and while compressing a piston cylinder arrangement, the temperature inside the chamber increases. But in order to make this temperature constant, there should be a sink which compensates this increasing temperature dt by absorbing the heat from the chamber. Then The second process is the reversible adiabatic compression, which is represented by 4 to 1. And in this reversible adiabatic compression is obtained by removing the sink. Why we remove the sink and place that insulation? Since this adiabatic process always occur if there is no heat transfer. So we are replacing the sink and placing an insulation layer at the bottom. Then comes the next process, which is process 1 to 2, that is the isothermal heat addition process. In this isothermal heat addition process, which is isothermal expansion process, when the piston moves up, the temperature lowers by a small amount dt. To compensate for that, there is a source which is supplying infinitesimal amount of temperature dt. And then comes the last process, which is the reversible adiabatic expansion, which is represented as 2 to 3. So these are the 4 processes occurring in a Carnot cycle. Now coming to the actual operation of a petrol engine. From the schematic diagram and the animation which is following, you will be able to explain how a petrol engine works. The first stroke is the suction stroke. For a petrol engine, during suction stroke, the inlet valve opens and through that air-fuel mixture enters the combustion chamber. And it is represented by this horizontal line in this PV diagram. The next stroke is the compression. During compression, as you can see, the inlet valve as well as the exhaust valve remains closed and the fresh air-fuel mixture which entered during the suction stroke is compressed. And then comes the ignition stroke. During ignition, the spark plug in a petrol engine supplies this higher temperature which is required for the burning of air-fuel mixture. And due to the higher pressure generated in the combustion chamber, as the burning of this air-fuel mixture, the piston moves down, which is represented by this expansion stroke or the power stroke. And the last stroke is the exhaust stroke, where the exhaust valve opens and this products of combustion are exhausted out through the exhaust valve to the surrounding. Now coming to the analysis of this Otto cycle. As I have already explained, this Otto cycle consists of adiabatic compression, reversible adiabatic compression. Then comes the isochoric heat addition. Then comes the reversible adiabatic expansion. And the last one, constant volume heat rejection. These are the 4 processes which are occurring for an Otto cycle. And you must know certain terminologies while applying Otto cycle. And these terminologies are, the first one is the compression ratio, which is represented by Rk equal to V1 by V2. The expansion ratio Re, which is equal to V4 by V3. And the last one, swept volume or stroke volume, which is equal to V1 minus V2. Now coming to the analysis of diesel cycle. The major difference between an Otto cycle and a diesel cycle is that the heat addition process for an Otto cycle takes place at constant volume, whereas that for a diesel cycle it takes place at constant pressure. The other process remains the same. That is, the first one will be the reversible adiabatic compression. Then comes the constant pressure, which will be represented by a horizontal line 2 to 3. Constant pressure heat addition. Then comes 3 to 4, which is the reversible adiabatic expansion. And the last one, which is 4 to 1, which is the process of isochoric heat rejection. That is constant volume heat rejection. And before ending, for a diesel cycle, there are certain terminologies. That is the compression ratio, which is represented by Rk equal to V1 by V2. Cutoff ratio Rc equal to V3 by V4, V3 by V2. Expansion ratio R equal to V4 by V3. And this Rk will be equal to, compression ratio will be equal to the product of cutoff ratio and expansion ratio. And the stroke volume, as usual, is the difference between V1 minus V2. Before ending, we'll brief about today's topic. Today, we have studied different laws of thermodynamics, the zeroth law, first law, and second law of thermodynamics. The terminology entropy was explained. Then the different cycles, Carnot cycle, OTTO cycle, and diesel cycle was also explained. Hope you enjoyed the lecture and see you soon.